And I'm going to ask each presenter to introduce themselves and maybe just give a brief introduction about yourself so we can move along quickly. We have a number of presentations to get to. Yes. Yeah, and anybody can ask questions during the presentation.
So my name is Kush Patel. I finished my master's about 6 months ago and joined data scientist immersive program in SF. This project is coming out from that project curriculum, and then I joined DSR here, the data scientist resident, and I'm here to help the students who are helping out. So basically, I'm the assistant to Dan. Dan is here, and so whatever he needs, I finish. And so basically, let's start with the presentation. So as a graduate student, I used to invest in a Kiva. So how many people know the Kiva organization? So very few people. So let's go to the Kiva organization. So Kiva is like a microfinance, non-profit microfinance organization which lends the money from the lenders to the poor entrepreneurs around the globe. Their problem is they do not have the credit system. Like around the globe, people will not have the credit system. And they have pretty good filters to filter out which loan will going to default or not, and they have to give a lot of choices to the people to lend it. But I found my experience, like past 3 loans, they were defaulted. So during my project, like during DSI, I found like, okay, let's build something that I can use and other people can use it. So that's a default finder. So using the data science, machine learning algorithms, I found that Kiva could have saved about $3 million using my product. So let's start from the beginning. So this is a typical page of the Kiva organization when you go to Kiva. So this is one landing page, like borrower's page, where there's a group of people who are asking for money. There's a description, how much money you want to lend it or donate it. So from these different loans, I extracted some features. Like there are about 21 features, but out of that I only showed a couple of them. So I'm just showing you what are the features that are available. I'm not going to jump into the machine learning algorithms, but I use different algorithms, and I found that gradient boosting classifier is one of the best algorithms to classify which loan is going to default or not. And since the default percentage, about 3% loans going to default. So if you use just accuracy and say all the loan will not default, you will get accuracy of 97%. So it's not a good method to classify. So I use recall and AUC recall and FPR to find to classify which machine learning algorithm is based. So recall is out of default on how many loans you can predict default loans there are. So and there is FPR is how many loans you are not predicting. You are predicting default but is not default. And then area under the curve is just basically the area under this curve. So here is the true positive, which is recall, and the false positive rate. And you can see the green line, which is like if you predict every loan randomly, that is a 50% line. So if your machine learning algorithm is better than random guessing, then it will goes above the green line, otherwise it will follow below the green line. So now I like more like financial side, I like it because I understand that machine learning is good, but if you cannot implement financial gain or what is the basically you can improve the company underlying profit, then it is not good enough for the company. So there are many different techniques you can use, but I use profit curve and cost benefit matrix. So basically I am translating what I learned using machine learning into the business aspect. So what is the cost benefit matrix? So cost benefit matrix is nothing like, it's very simple. So if you predict a default loan as a default, means you will save some money. If you predict a default loan as non-default, you will lose some money. as well as if you predict non-default or the default loans, you will lose some money. So there was some assumption I made, but I calculated this cost-benefit matrix. You have to remember this is microfinance loans. So the minimum interest rate is 36%. It starts with 36% interest rate. So interest rate is very significant. Average amount is $408, and I use interest rate. And then I also did some analysis to find out how many percent will churn if Kiva will not able to find out which loan will default. So basically, if your services will not able to provide enough good service to the customers, they will gonna churn. So I also included that number into this cost benefit matrix. So I use the loan, interest, and churn cost. And if you credit default loan or non-default loan as non-default, there is no extra gain you are getting out of it. So it's zero. So the profit curve. So basically, you use cost benefit matrix and ROC curve to calculate the profit. So on average, there are about 907,000 loans lended by the Kiva. On average, I found that using this profit curve, you can save about $3.32 per loan. So if you calculate, it's about $3 million, and that's my presentation. Yes.
Did you parse the text of the loan requests to gather your data, or how did you get?
So the question is
data out of a predominantly qualitative.
Okay, so the question is what I did with the text data. So basically, I was like people who are borrowing the money, they are not literate enough. So how many people know the Kiva's working style? That is associated with the question. So I'm going to ask. So basically, what is the if you lend the money, it goes to the Kiva. Kiva lends that money to the working partner in that country, and that working partner will lend the money. Okay, so the borrower goes to the working partners. The working partner will write that tax and put it on the Kiva web platform. And already we have the working partner information, so it will be just replication of the tax. So I did not include it. Yes.
Well, you said you used interest rate. What interest rate did you use?
So minimum interest rate in the microfinance from the Kiva platform, it was 36%. Minimum. It starts with 36%. So
36%?
Yes. It's a microfinance. It's like very small loans. So it's not like US. I don't know what the percentage is here, but it's 30. So I assume it minimum interest rate, which is so at 36%, Kiva will what do you call? They will not profit, but it will not lose any money. So I use that one.
You know that 36%, is that what the lender pays, or is that what the excuse me, is that what the borrower pays, or is that what the lender receives?
So there are two types of lenders basically. So one is the partner. So the partner also gains the money. So basically, I am considering all three participants: Kiva, what the lender will get, and also the people who are working in the partners basically. So all three combined will have that impact, not the single person. But the borrower will pay minimum 36%, but the profit will be distributed over three people.
So all three parties split up that 36%.
Yes.
Okay.
Yes.
You mentioned originally that there were a number of different features you could chose.
Yes.
You would have, there was a geolocation-based one.
Yes.
Could you explain just a little bit about what you used for feature reduction, what process drove you those specific points?
So basically, two things I did to find out which features are most important. First is the EDA, exploratory data analysis. I plot a lot of stuff, and I found out I'll say not event, but situation was very interesting. There is a country near New Zealand, I forgot the name, but out of 5 people, out of every 5 people, 1 person is borrowing money from the Kiva. And another thing I found that even though I recognize Kiva as lending money toward Africa, the major borrower is Philippines. So you have to do a lot of data visualization to find out which features are very critical. And also I did a little bit of feature engineering, but mostly you use tables you do a lot of visualization. That's the main aspect of it. Yes, any other questions?
question, following up on her question. Is the data you used, is that publicly available?
Yes, it is publicly available under QI API. So I had a question. So let's say this is the machine learning algorithm. Now I am predicting only default loans on QI is working on. What are the steps you will take to find out if QI is entering in a new country or new market? This will machine learning will not work. So what steps you gonna take to make sure that it's working the way it should work for the new country? Anybody? Simple answer is, so basically I'll say the simplest way is remove the geolocation information, basically the country name, partner ID, where are the location. So basically you are trying to nullify all the information about the geolocation. Then you try to predict the default loans, so it will give you the more information without geolocation bias, geolocation information. So you will be able to predict it for different country where QI is never based before. Yes.
So how were you able to predict that the loan was going to be default? I know you're saying you're using machine learning and
Yes.
various statistical analysis, I'm assuming, but so what was it based out of?
So basically, once you have a data set, you split it, train and test,
Right.
and you do cross validation to see how well your model is working.
Oh, okay.
What was the single biggest predictor of default that you found?
So then, let's split down in two sections. One is with the geolocation, like all the geographical location, and without the geolocation. So if you are considering geolocation, then geolocation is one of the biggest factor, like the location of the money. Yeah. So for example, in Philippines, there are a lot of borrowers, but base likely will default. But if the second most highest country who borrowed the money was Zimbabwe, but it was one of the highest default loans, default rate from the around the world. Another thing is for if you remove all the geographical location, country name, and stuff, I found that loan duration and loan amount was the critical.
And with longer durations are more prone to default or less?
That one I was not able to finish that one. Yes.
So could you use clustering if you remove geolocation or put geolocation as use clustering to see things?
I did not do the clustering because my main target was prediction rather than visual inference. So I try to make it a little bit simpler.
But if you took geolocation out and took two different variables and scatter plotted them, you should see no correlation, right?
You should not able to see the correlation. Yes.
Did you look at all, determining what interest rate would then be profitable due to the risk profile?
No, I do not have time to do that.
This may be the same question. You said Zimbabwe had the highest rate of default. So is then your recommendation not to lend in Zimbabwe, or is it to raise the interest rates so that you can cover your default risk?
So I only reach until the business aspect, like what are the financial implication it is. I did not able to do further steps like that. Yes.
How do you handle the temporal aspect? So you might not lend to Zimbabwe at the moment, but if Robert Mugabe died tomorrow, the country is probably might improve.
Not able to hear.
Sorry. How do you handle the temporal aspect? So Zimbabwe might improve tomorrow. Or you might not lend to Syria today, but you might do next year.
Yes, so if you don't use the geographical location,
If you do. If you do a job for results or something.
so basically I haven't covered this one. So basically there is a techniques called online machine learning. Those kind of work will much better with the kind of you are asking about, like how with the chain. This is a static one. So if you are considering about as the data is coming up, you are modifying your machine learning algorithm, then it is much better to use online machine learning rather than statics one. Yes.
So if we talked about this at the beginning, maybe we can expand a bit. You said Kiva didn't actually end up taking the model and using the product very well. They give you a good explanation as to why they didn't take it up? Because even looking from a developmental perspective, you would think $3 million would do a lot of good.
I'm still talking with them, so.
They just kind of didn't know what it was.
So I think the president was on, like CEO was on break during the last 2 months. Any other questions?
Yeah, thank you very much. Sam Triolo. Close, Triolo. I'm sorry, I mispronounced that. Sorry, Trio?
Triolo.
Triolo.
Don't ever try to say it. It'll get you
Hi, everyone. Okay, so, and I'm going to get crossed back over there in a second. So I'm Sam. I have been working in information security for a little over a decade, and I decided I actually came into data science in backward ways. I've been looking into something called computational neuroscience, which is really cool, and it's kind of it's a whole other topic. But data science has some good foundational stuff that would lend itself to that, and data science is probably the current computer architecture's best way of trying to process information. So that's how I got into it. My data science knowledge is pretty much limited to the project that I'm about to show you. I could probably tell you a little bit more about computational neuroscience, but that's not what this is about. So for any of the advanced questions that some of you are thinking of, like what about the temporal aspects of this, I'm going to give you a blank stare on my face in response to the question. So if you have a direct question about this or about security or computational neuroscience, I'm happy to answer it. Well, computational stuff, neuroscience, the best that I can. What this basically talks about is, in information security, one of the things, there's a lot of different information that you can process. One of the great things about computers and stuff like that is there's a ton of structured information or semi-structured information. One concern, of course, working in security, I work internally for a financial company with about 170 billion in assets under management, is whether or not you have hackers or malware that are active on your network. So we have all sorts of devices and alerts that got me up at 3 in the morning this morning, telling us when there might be a problem. They don't catch everything, sometimes they miss things, and what they miss you don't know. One of the common, what's called attack vectors for various malware and hackers is to basically get to the point where you're installed on a machine and or where you have compromised a set of credentials. So this is something like a username and password. A lot of companies have what's called single sign-on or transparent authentication. Once you log into your machine, any other machine that you have the access rights to access, and any other application you want to access, you can just do so. All the authentication happens in the background, you don't even notice it. Kerberos, Active Directory, for those of you who are so technically inclined. So hackers and malware will go after this to try to basically use any of the rights that you have to install themselves, to wreak havoc on other machines, to siphon data out of servers and stuff. If you're a financial company with hundreds of billions of dollars in assets under management, that would be really nice to get a hold of. If you get a hold of an IT admin's credentials, someone who can access any server in the company, like me, then that would potentially net you a ton of money. So there's an interest in trying to figure out, okay, what malware did we miss, and how do we find that we missed it? So that's part of what this tries to do. So who are we looking for? I talked about already the bad guys, hackers and malware. How do we find them? Like I said, this was kind of my crash course into data science. So I used unsupervised k-means. It's really simple conceptually to understand and to implement. And I wanted to understand what I was actually doing, not kind of plug something into a black box and hope that the results came out right. The great thing about k-means is you can generally, let me grab this whiteboard over here. So the great thing about k-means is that it's going to put stuff into clusters, if that's how you design it. And let's say that we've got two clusters, one right here and one right here. And let's say you've got members of the cluster like this, and this is the center of each cluster, like this. The real value that I found in k-means was twofold. One, what we're looking at is, sorry, I should have said this up front, what we're looking at is user behavior. So we want to look at any user logging into any system, and I'll go into this in a second, and basically say, okay, is there something that we should be concerned with here, some pattern of behavior? So we can look at that two ways. One, I already knew this from working in my kind of job for a while, that users will fit different profiles. Someone who is working in marketing will never log into any server. So if you see someone in marketing log into a server, that's an anomaly. That's probably not right. You should look into it. There's other users who have exceptions. People who work on the desktop team that fix other people's computers. They get calls from someone in marketing saying my machine's not working right. Take a look at it. They log into that person's machine. You will see that person's ID, the desktop team, touching workstations, like normal people's laptops all over the company, but you should never see it touching a server. That's another profile. So IT admins are the reverse. They'll be touching tons of servers, but you should never see it touching a workstation. So I know this, right? So no, it's okay. I'll take it. Marcus is better than one. So the advantages of the k-means algorithm is two things. One, you'll start to see these profiles show themselves, especially in usage behavior. You should see users only logging into their own laptop if they're the marketing person. You should see the desktop IDs logging into other workstations but never servers, and the other examples that I gave you. So when these profiles start to show themselves in the patterns of each user showing up in certain clusters, if one user is in a cluster that you don't expect them to be in, that's warrant for further investigation. You want to find out why that is. A big thing in security is you don't want anomalies. You don't want something that's out of the ordinary. A lot of very big security hacks begin with, that's odd. And then you dig a little bit further and you're like, holy crap. So one thing is group membership that you're going to look at, and then another thing is just outliers. So if you have an IT admin or a desktop person, even if it's a desktop person that's supposed to be logging into other workstations, but they're logging into 10 times as many workstations as other users, that's a problem. Now, these threats aren't necessarily, the way that I've talked about it, these are credentials that have been compromised by hackers and malware. It could also indicate someone who is nefarious internally, right? And they're hacking, you as an employee. So those are the two things that this will help you find. So the way that, I guess the titles aren't showing up here. Yeah, sorry about that. There's supposed to be titles at the top of this. I don't know why those didn't show up. So the way that I gathered the data for this was, I prefer to deal in Linux. Unfortunately, a lot of corporate environments are built, probably the majority, are built with Windows. So I had to delve into VB script, which made me feel a little dirty, and it was. But it is probably the easiest way to harvest information from, or one of the easier ways, using Microsoft's native languages, .NET, etc., to harvest information. These do not live in any centralized location, I would come to find out from my research. These are hosted on every machine, so I basically had to touch thousands of different machines. There's other things that I came into contact with. You generate a login event every time you pull a certain set of logs from that machine. So by eliminating the ID that I used to pull the logs, I eliminated like more than 60% of the log data itself that was generated, which totally increased the efficiency of the analysis. The events that I was able to settle on, for those who have way too much time on their hands, are 4624 and 4625. Microsoft AD, login successful, login denied. Used Python to do all the, as soon as I got it, I really just used VB script just to pull the raw data. As soon as I could get it, I wanted to run for Microsoft as soon as I can, so I moved it over to Linux and did the rest of it there. Python ETL, MongoDB, Scikit-learn, which was great, has a lot of great algorithms for those of you getting into it. If you're trying to figure out which set of libraries to learn, I think Scikit-learn is probably the most mature from what I've found. IPython for data visualization. I do this personally and it worked too. I prefer to have a machine with a lot of horsepower and a lot of hard drive space and not tie it to my personal machine, so I have a server set up remotely. Boca allows you to do the visualization remotely and be able to do things like zoom in on certain areas, pan, zoom out, things like that. So the main features that I use for the analysis, unique destination logins. Oh yeah, it was workstations and servers is what I was looking at, which was determined by IP addresses and host name conventions to determine, whether it was a workstation logged into or a server, the source and the destination. Total logins, and then the following features at the bottom: workstation to server, server to workstation, workstation to workstation, etc. And then, because I work in a financial organization which can easily afford a team of lawyers to shred me, I've decided to not post the data that I actually found internally. So instead, you guys get a plot of the IRIS data set, which is very popular and very easy to use. Basically, what you'll find is kind of what I described over here. I found, certain profiles that would develop. A lot of the average users were clustered very tightly together. They were doing things you would expect them to do. And then occasionally I found some users that would stick out for one reason or another. Some users were very heavy VPN users. Whenever they took a break, they would shut down their laptops as a result of that. When they came back online, DHCP would give them a new IP address. That would add noise to the situation. It's something else you could adjust to, because the next thing would be to figure out what normal VPN, traffic is, so that you can figure out even outliers among that group of people. IT admins had really high login rates to other machines and things like that. To some extent, if their ID was compromised, it would probably be very difficult to find, because some of them touch a lot of machines to begin with, so you may not really know very well. But yeah, I was able to perform investigation of a number of different IDs and determine which ones were warranted further concern and further investigation. And my next step potentially is to try to put this into a supervised analysis and then figure out thresholds where alerts would be triggered. Basically saying, okay, here's the usage profile for this type of user. This other user that we found, user A, fits inside that profile, but they're an outlier, or they're in a profile they're not supposed to be in, and you should investigate further. So that's another great thing about k-means too, is you can turn it into a supervised version too. This is what I told you guys about before, the two main advantages of using k-means. Developing user profiles and determining what profile someone should be in or not, and looking at outliers, people that are unusual within their own profile. And then these are some great resources for digging into some of the stuff if you want to, some statistics stuff. I find this all the time, which is another reason to not like them, but usually the best documentation for Microsoft is not done by Microsoft. They have no real information on how their event logs are structured. This reference that's in the middle here, they do a really good job. They have the best information out there. There's a lot of really vague and fuzzy stuff in there. I had to get on a number of calls with Microsoft using, thankfully, our existing support contract to get their experts and actually get some details out of them. So it's a little bit opaque. And then, yeah, the k-means, simple example. That's pretty much it. Questions?
So, two of the structures were fairly close together.
Yeah.
In retrospect, if you were to do this over again, try to replicate it, do you have any idea of things you might do to try to increase the margins of those targets?
Yeah, I mean, like I said, this is just the IRIS one, but of course there were other ones who were closer together. I mean, it kind of depends. This is kind of a cheater's way to do it, but you can zoom in. You know what I mean? I mean, basically, the clusters are close together because if you have, there's a number of users that only log into one machine. It's the machine that they're going to be using for the day. So there's going to be a lot of, users that are kind of close together. So I mean, if you zoom in, the space might become more apparent. You can also you know, this comes down to actual numbers, of course, to perform this analysis, so you can set your own threshold of what data you're actually interested in and not plot the rest of it.
My question was similar. What measures did you use? Here we're looking at Patel data. You're going to set features, but like what numbers specifically?
So this was an, if I understand your question right, this was an unsupervised analysis, so I was actually looking for it to tell me what it thought was significant. So the way the scikit-learn algorithm initializes itself is it will basically pick a random point to begin with, and it will assemble the cluster centers based on that starting point. And that's basically, for those of you that don't know, that's basically how the k-means algorithm works. The center of each cluster is determined by the average of all the points in the cluster. So if you add a point that's, let's say, for some reason way out here to this cluster, it will move this cluster closer to it, effectively, the cluster center. And then any points that are closer to it now, it does a recalculation on all the other points and says, okay, are there other points that are closer now to this one than they were before, that were originally members of this one? And it will recalculate that. I think that's technically an NP-hard problem. So they do, the scikit-learn does 10 initializations of it, I think, and takes the best of them to plot it. I also use, I didn't mention this, but I used PCA for dimensionality reduction, because technically it's 6 features. So.
It was the random, whether how you initialize it was my second question. The first one, I guess looking at, you got pedal width versus pedal length here, right?
Yeah.
And so I think it attaches a little bit to his question, like the measure that you use to actually establish those clusters will give you essentially the ability to, I mean, if you were to use something that's logarithmic, you're looking closer together, like you use a measure that they were more exponentially based or polynomially based, you might be able to see them move further apart. I'm just numbers show up in your n-dimensional space for things. Because you're talking about like IP addresses, right? And like people logging into them. How do you establish a measure, which is
it's a count. It's a sum. So I basically summed the number of times that, in this case, maybe I understand your question a little bit more. In this case, I was counting the number of times people logged in from various sources to various destinations. It was no advanced mathematics on this. If a user logged into 8 servers, if it was like I mentioned, I had both unique and total as some of my features. If they logged into 8 unique servers, that feature would be 8 for them. If they logged into 4 different servers, a total of 8 times, then unique would be 4, total would be 8.
So instead of, so his question right there, if you want to spread the cluster spread apart, you have overlap. For instance, you might use a better that is exponentially based, and then you have
Yeah, for sure. That's true. Yeah. Go ahead.
So you brought a certain amount of your own experience to this and how to calculate that group of that type of user does this and doesn't fit this type of behavior. And looking at the data this way, did you learn any new things that you didn't know about types of user? Did you build any algorithms that help you discover new types?
The second question I'll answer first. I am looking to build into follow-up depending on how much time allows to do kind of more detailed analysis of this and put things aside. Part of the reason, besides the fact that I'm busy, that I haven't chased it, is the answer to your first question, which is I did not find a lot that surprised me. We have a pretty small employee base. Our employee base is about 1,100 people. So that's not really that sizable. I mean, there was nothing really that stuck out in the analysis. There was, all the people that I expected to have high touch on a high number of machines were all IT admins, so.
Do you use the same type of techniques on emails?
Well, I mean, the answer to your question is I have not built anything to inspect our emails. We use a few different appliances. There are some, I'm sure they're probably using data science in there to do that, to sort spam from otherwise. Some of them, one of the really popular devices is one called FireEye. What it actually does is with any attachment that it sees come in, it spins up a virtual machine instantly, detonates the attachment, waits for it to infect the machine, and has a rootkit that it built inside itself that tracks everything the malware does, and based on that behavior determines whether it's a virus or not, and it doesn't like that. So that's both signature and heuristic based. So those companies are getting pretty heavily into that stuff.
Did you ever get to the point where you could actually recognize that a little piece of data was actually a person? So like you recognize your own data because of your own usage habits, or you guess that was Susan and counted like down to an individual person instead of just a group?
So yes. When I plotted this in the real one, I set it up so that it would plot the usernames next to each plot point. So that way I wouldn't have to dig for it. that was the easier answer to that. But also, there are a few IT admins who we know do a lot of heavy lifting. There's also, I touch a lot of machines. I do a lot of the vulnerability management internally. So I am touching a lot of machines too. So that data showed up. Yeah.
So if you didn't have usernames, you could guess that was you and your friend Bob.
I don't know that I went that far. I don't know that anyone was so unique, but I could guess that it was one of a handful of, like the outliers in the IT admin group. I had a feeling it was going to be one of a handful of people, and it was. But no, nothing where I could just guess the user without the username straight up. No, not really. Oh, sorry. Actually, I think Cheryl was first.
How did you determine the right number of means? How did you come up with the right cake?
That's a good question. I chose one randomly. I thought that was a very educated approach. I basically toyed with the algorithm a little bit. I just input, this is supposed to be like one of the Python work ethics. I just went with something, and then I added or subtracted to see when it started to come up with something that was less meaningful. If there was a cluster where everything was super tight together, and I had separated it essentially into two clusters, even though they were basically overlapping, then there was really no point to it. So, and I had a small enough data set where that was possible. If you're doing something really huge, you can't just be changing that stuff. Go ahead.
So the other question was, I think it was KDD Cup, or 2003 was basically this challenge. The data set, you can download it online. So you ever thought about like getting another data set and trying to, because that's a much bigger data set over a bigger network?
Yeah.
Have you ever tried to doing that and see, hey, look, can I stretch that out?
No, not yet. I haven't tried to do something bigger yet. I'm kind of, a lot of my time, I'm kind of getting into both at the same time. I'm also trying to write a novel, or trying to finish a novel. So I'm doing the computational neuroscience, the data science, and the novel. So it's tight. We'll see. Go ahead.
Well, behavior analysis is all good. Have you thought about including database comparison between who's online, who should be clocked in at the time, maybe kicking off a user if they're signed on a machine as opposed to another, enable anybody who's high profile or something on machines like yourself?
So those are all valid potential approaches. In terms of kicking someone off a machine, I don't know if you've ever worked on Wall Street, but there's a certain amount of fear involved when someone who makes tens of millions of dollars a year is pissed off because you decided to unilaterally kick them off something, either because you thought you had good reason or because there was a bug in your code, and then you find yourself jobless. So I would probably never be able to institute that. I would never even be able to get that past my manager, nor would I want to even try. So probably not that one. But yeah, all the other, these are very, working in finance and in Wall Street, so to speak, because they're trading, they're trading actively. You're very sensitive to the user. This is like a white glove approach. You're supposed to be considered like 5-star hotel guest service. You do not do that.
Sort of automated service to weed out as many as you can.
Yeah, you would not do that. No, you would. The easiest way for you to quit your job would be to get too aggressive with that. So, go ahead at the back.
Keeping in that vein, then, on the plus side, how did you convince them to let you work on this project, their data? On the looking forward, what sort of challenges do you expect or have you already encountered with getting them to trust something like this as a potential product in the future?
So the only real potential for impact was me pulling logs from the host machines. I did the analysis on a server that I built. I build all my own servers and maintain them and stuff. So I mean, that wasn't going to hurt anybody. If I was doing something where you're, say, deleting information or doing something that can really impact users, then you really do have to be careful, and I would have to run it by a number of people before I did it. Because I'm essentially performing a read-only operation, and it's fairly low bandwidth. I mean, you pulling the logs off a machine is not a lot of load on the machine, CPU-wise or network-wise. I mean, the risk was really, really low. Plus, I've been doing some of this stuff for a while, and they know some of the code I write. So unless I was proposing something really risky, I don't think they'd be super wary. In terms of what can be done in the future, that's what I've been spending some of my time looking at, is the next analysis that I would build. I'm debating whether I should go deeper on this one and do something supervised and add more features or add more automated blah, blah, blah. One thing that I have found, this might answer your question too a little bit, is that before you go really deep into something, you should figure out the utility of it. Because a lot of times 6 months later, you found out that it doesn't really add a lot of value, and no one, including yourself, is really interested in using it anymore. So right now I'm going broad rather than going deep.
It's words where you're less than
Yeah. Yeah.
What about looking at system accounts or local accounts on computers? Does somebody compromise that interfere with the app?
Yeah, you could do that. We, as a policy, we have local accounts disabled, and you can't really create them. But that doesn't mean that it couldn't happen unintentionally. There could be a break somewhere in some automated system that maintains that. It would probably be good for us to find out whether there were any local accounts that were existed on machines. That would probably be more a concern than anything else. But there are system accounts that are not local. Matter of fact, that's what most of the IT admins use. They basically use a domain admin account which can access any machine. Go ahead.
Curious about computational neuroscience. Do you have a short synopsis?
Do we have a minute? I'll give you a computational neuroscience is basically the von Neumann architecture is the computer architecture that all of you are familiar with and don't know. It's the one that's in your phones, it's in your PCs, RAM, motherboard, CPU, which has an ALU in it, blah, blah, blah. Computational neuroscience is basically processing information like an organic brain. Neural net is basically taking the current architecture and trying to make it like a brain. Computational neuroscience is actually completely different hardware. It's assumed that you will build a neural net on a discrete processing system with ones and zeros. With computational neuroscience, all the computations are performed by minimum populations of neurons, and it's based on rate timing, frequency, all sorts of stuff that actually the computations are done basically not digitally, right? They're not ones and zeros, they're analog, right? They're frequencies, populations, it's not definite at all. It's entirely different, right? It's fundamentally different. What's that?
Almost like qubits.
Yeah, it's not like a qubit in a sense, but it's as fundamentally different from the current architecture as quantum is. So if it works, it would be massive. They've got one called Spawn that's been built. It has 2.5 million neurons. It can see like really rudimentary objects, can remember 7 objects, and has a virtual arm with like 3 degrees of movement. Doing 30 seconds of simulation time with that 2.5 million neuron thing is 2.5 hours for every 1 second of simulation on Amazon's biggest server. So to get an idea of how much information your brain processes, you have 100 billion neurons, which would probably take every server Amazon has to even simulate one of our brains. That's how much more powerful your brain is than the architecture we all think is so powerful that's in your hand.
And it consumes 5 watts of electricity.
Yeah, and the power consumption, so it really makes the current device in your hand look like a piece of crap. If we get it to work, it would be...
Thank you, Sam. Can you tell us what your novel is about?
Surprise, surprise, it's science fiction. I know you were expecting, romance, but no.
Does it have a security aspect?
No. One of my novels does have a little bit of security aspect, but because I've got so many interests going on, I had to kind of pick one and go with it. The one that I'm working on does involve the fact that we bring Teddy Roosevelt back from the dead to help save humanity. That's a little teaser. I know you're all interested. So Alexander the Great too fights some great battles. It's pretty epic. That's great. Thank you, Sam. Okay, we now have Kamal from Cloudera. I want to make a special thank you to Cloudera. They're one of our sponsors. They're wonderful people there. If you get a chance, afterwards talk to Kamal. Megan is back there. You can talk with her. She's very friendly. And I just want to say thank you very much to them. They're not only is it a great company, but they're just great people there as well.
Hi everybody. Just give us a 10 second. Yeah. Something else. So, what a beautiful space, isn't it? How's everybody doing? I get to watch the beautiful space and you get to watch me. So while we're getting the slides up. So first of all, you notice that I kind of fizzled the slides. The topic is supposed to have been stream processing. I felt like 20 minutes just wasn't enough time. Oh, 20 minutes just wasn't enough time for any kind of serious technical topic. And I realized amongst many of you are better suited to do the technical talk on stream processing than I am. So instead, I realized a couple of years ago when we were starting the new user group for Boulder, Denver area, we were having these meetups every month, and there are various topics that are being discussed. About 3 meetups later, people realized, you know, it would be a good idea to do Hadoop 101. So we're talking all these topics, and people aren't even grounded. What I hope to do today, and by the way, this is from loan. Most of the slides are on loan from our data science director, Sean Oden. So what I hope to do is kind of create that basic understanding. What is the data science? I mean, so much sensationalization that has occurred for data science that I think it's a good idea to understand what it is. So I noticed somebody asked early on how many data scientists are here, and only 1 or 2 hands went up. How many are participating in the hex key competition? Not good. We need more.
What is this?
You need to know what that competition is going to be about. So maybe if you haven't decided yet, this would be a good way to learn what it will be about. I'm actually looking forward to whatever you guys will create, or whoever the competitors will create, so I can choose which day to go skiing on which slope. I'm assuming everybody knows what the competition is about, right? Okay, good. So with the data science sensationalization, you see, and by the way, these are actual headlines. So all kinds of I like that one. How many want to be data scientists now? So clearly there is a lot of interest in what data science is, what they do. It's a bit of a mystery, and I know Michael has done a great job of kind of creating awareness and education about what data science is, and he can tell you a lot more than I can. I don't identify myself as a data scientist, and you'll know why, because I know what the slides are about and what makes up a data scientist. So with that, I wanted to just quickly what I plug in for my company, Cloudera. So Cloudera, most of you probably familiar with Cloudera. We're the Hadoop leaders. We've been around since 2008. A lot of innovation, a lot of influence in the open source community. I would be surprised if somebody still hasn't heard or used the Cloudera in some way or other. Just as a show of hands, how many people actually use Cloudera CDH, Enterprise Data Hub? Okay, we need more hands. Seriously. All right. So the original slide deck was much larger, and clearly in 20 minutes or 15 minutes we can't do much. So what I intend to do really is just kind of go through and make it a little more fun. So I was thinking of making it more like in the style of Who Wants to Be a Millionaire, make it more like Who Wants to Be a Data Scientist. But then I realized if people don't even know what it is, then you can't really play that game. Everybody knows what a millionaire is or looks like, right? So let's just focus on two topics. What is data scientist, and what exactly do they do? Why is it such a, one of the headlines was sexiest job. All right, any questions? Is this a good topic for everybody, or were you really expecting serious K-means clustering and regression or whatever? Well, if you were, then sorry. So, next few slides really just kind of poke fun at what data science to different people is. All of us can relate to being a data scientist of this kind, right? We extrapolate all the time. Some people think data scientists live in California. Now, with the number of hands that are going up, this may actually have some truth. That's why we need more hands going up in Colorado, but clearly this is not true. These are screenshots, so just so you know, these are not made up, right? Somebody actually believes. Maybe they're poking fun, but the fact is, it's just not as well understood as it should be, and hopefully you walk away from here thinking a little bit better understand. This seems to come a little bit closer to what data science is. Little bit of programming, little mathematics, some domain knowledge. The Venn diagram kind of comes close to what data scientists are.
He is great.
Everybody can see it?
Yeah.
Some people, and especially the business side of people, they think, hey, I've got lots of data, and in order to make some profit out of it, I need data scientists. And believe me, I'm in sales, right? So I talk to a lot of customers, and this is what I hear. We need more data scientists. Do you know what it is? Well, this is what it is in their mind. I have lots of data, and now I'm monetizing and make money. Well, clearly, every company's goal is to make money, but you have to understand this is a different breed of trade, of people, mindset. It's sort of like when you coming from databases, traditional databases to Hadoop, it's a different mindset. You don't think of rows and columns and this, that, and other. It's much more wide, free-flowing structure, unstructured, all kinds of stuff. Data scientists, or the type of things that data scientists enable, needs to be looked at in that sort of sense, in a very clean slate. So, Josh Wells, one of the well-known data scientists at Cloudera, actually came up with this definition, which seems to make a really good sense. So data scientists are better statistician than a developer, and better developer than a statistician. Makes sense? They need both, but they are not what you would call serious software developer or a statistician making all kinds of statistics and model. They just need to understand what statistics is and what it does and what a model is. be able to use some of the tools and the packages and software and make something happen that is valuable to the company, valuable to society, community. Data science clearly has a lot of promise, and I think once we understand what they do and how they do it, I would hope many more hands go up the next time. So with that, just kind of reiteration of differentiation between data scientists and software engineers. So software engineers, most of them don't understand what the statistical assumption of a model is. You give them a model, K-means clustering, for example. If you give it to them and explain what the algorithm is supposed to do, they will code it. They will create a software or package that will do what you ask them to do. But they don't know what that means. What is this clustering? When somebody asks, well, what was the K and how do you come up with the right K? Those are the types of skills that data scientists, a person who wants to be in that role, should understand. So they don't need to write a book on either software development or statistics, but they need to understand both. And clearly some domain knowledge. So for example, very famous, you must have heard of Simpson's paradox. No? So what it is if you take enough data and analyze it with some standard linear regression, for example, you will miss details because the data is going to be all over the place and it looks like it's just normal regular data. But knowing and looking for things that are hidden in that data can completely change or reverse the outcome. There's a very famous case, UC Berkeley in I think 1950s or 60s was taken to court because they said that they were discriminating against the women in entrance or as they applied. And the initial data set or the analysis actually showed that maybe there is some discrimination. But when they looked further and deeper on aspects of certain departments get a lot more male applicants, certain departments get a lot more female, and the affinity of people pursuing these degrees, they were able to prove that it was actually in favor of women overall, and not the other way around. So just a fact, this is just to say that with that statistics understanding in mind, that's what you need to bring to the table when you are in this sort of a data science role. So, a little bit about data scientists, what kind of breed they are, but what do they do? So, according to Sean Owens, our data science director, the primary role of a data scientist is to create data products. So, what is a data product? Clearly, it's created from data. So, it's all about data. You have data and you're doing some analysis, extraction, modeling, whatever. But the important thing is, this data product can be improved and extended by using more data. So unlike an example like, say, a waffle iron. Now, you can collect all the data you want from the waffle iron, but what kind of changes or improvements can you make? It's still going to make waffles. And by now, we've basically created a waffle iron that just makes really good waffles. But with the data product, the more data you apply to it, you get better and better and better at that, whatever that data product does. If it's analysis, if it's prediction, whatever it is. So that is the key differentiator of data product. And obviously, a lot of it, so people talking about machine learning, so automation to bring, so it doesn't have to be a person doing it. You can apply the machine learning algorithms, with the data that you have and make it improve it, make it better. Some examples. So data products is actually not new. Obviously, in the financial industry, they've been doing this kind of credit scoring and fraud detection and mitigation for quite a while. But what has changed is, while initially they might have been doing it on a spreadsheet with maybe 1,000 records or customers, they can now do millions, millions, maybe billions. And every time they add more, their modeling capability, their prediction, their analysis is getting better. That's what you call data science or data product. Another example, so machine learning, data scientists, all of these words are generally used in the context of big data. And I'm sure everybody's familiar with big data. Traditionally, you will see people talk about the volume, variety, velocity as being the big data. I talk to customers, and the first thing they say, I only have 10 terabytes of data. I don't have big data. All they're talking about is one of those three, right? Mostly volume. So it isn't just that, it's the interconnection, the relationship of that data, which, as you can imagine in a cube, if you start with just the few dimensions of data, suddenly with the interconnections and interrelations, it explodes. And that's what makes it kind of interesting and compelling. I mean, when you're going to work with data and create data products, you want to be looking at connections to the data, relationships to the data. Another example, sort of everybody's obviously shopped on Amazon, I'm sure, and they started at least 10 years ago, this recommendation engine, 10, 12 years ago. So because you may have bought 5, 10, 15 things from Amazon, as a whole, Amazon knows about millions of those products and purchases and transactions. They are now able to apply that knowledge clearly on a fairly automated manner to say, oh, if you're buying a blender, you might want to get something else because 50,000 other people were interested in this. Obviously works. That's what you would call data product. They are using it to their advantage, and the fact that it's not just to their advantage, right? I mean, as a consumer, I like to know if I'm only looking at one thing, I like to know what others might be interested in, how it correlates, and maybe I'll make a purchase. Actually, I have done things like that just based on the recommendation. Another example, so Google, everybody remembers, Google started with a very, very simple search interface. You type a keyword and it searches whatever it does at the back end. After about, so it was in 98, after 15 years or so of Google having to keep doing it again and again and again and again, with billions of records, now you see Google starting to do spell correction, look ahead typing, or type ahead or completion, right? All those features are coming in because they have so much data that they can now start to build features that people will like, benefit from, appreciate. So those are just examples. So by the way, I just actually added this slide because I liked the picture. Whenever you see leopards on starting out. But anyway, the point here is, clearly the picture is good, but data becomes your new competitive advantage. It is the competitive edge. So, get serious about learning about your data and what the data products that can be built, how you can help yourself, your company, your community, and so on. That's really the message here. And finally, another very famous experiment. Can anybody identify what that is? what is some kind of a plane? You got it. It's a gossamer condor. In 1950s, I think late 50s, this gentleman, industrialist from UK, said, you know, I mean, obviously he had money, 50,000 pound reward for somebody who can have a pilot powered, so they didn't call it pilot, so just a man-powered airplane that can travel. Actually, the competition was to do a figure 8 at about 10-foot height, and the total distance was about 100 feet. That was the competition. And of course, 50,000 pounds is a lot of money. Even today, it's like almost $1.5 million. So multiple teams tried and failed, and tried and failed. It wasn't until mid-70s, 77, McCready said, let me look at it. I mean, clearly money is there, and that's very attractive. But why is everybody failing? And what's going on? I mean, it's got to be doable. What he realized is they were solving the wrong problem. The problem just wasn't that you can get up in the air and stay up for 100 feet, because it's going to take iterations. You are not going to build this machine, take it, roll it up to some beach, and think it's just going to fly, right? There's going to be crashes, then you have to rebuild. Everybody else, so McCready looked at everybody else's failures and realized that they were not building it for iterations. So they were building it, nice and tight, and a really good looking machine, and 2 minutes later it's crashed. And it takes another year for them to rebuild. So he decided to experiment with materials that are obviously easy to rebuild, retrade. He used mylar or plastic for the wings, aluminum tubes for most of the structure. And of course, it wasn't like he was successful the first time, but he went there and tried, crashed, came back with a fairly modular design, so he was able to repair quickly. Within a year, he actually won the competition. So what's the lesson here? With data products, you have to design them for iterations. You don't expect to create a data product which is just perfect the first time you create it. You start somewhere, and obviously the whole software design is heading in that direction of iteration and so on. But so that's kind of the key message of this experiment, which was almost 60 years ago.
I was going to say the Wright brothers took exactly the same iterative approach.
That is true. Yeah, absolutely. So they actually took it even one step further, and that's when we started to have sort of a dream commercialization of this machine is possible. McCready was just wanted to get the money, right? So he did what he needed to do, and he showed that it's possible. He got the money. But so the idea is it's an iterative process, and so kind of start with that mindset. So if you want to be a data scientist, start thinking about data products. Clearly, you're going to have some kind of programming, hacking skills, some statistics, some domain knowledge, but most of you are in some way or the other in technology already. So 1/3 of the equation is already solved. Now it's the statistics, so start taking some classes in statistics. Can't be that difficult, right? And then by doing it, you will certainly get the domain knowledge and you'll make some successful data products. In fact, as I said, I'm really looking forward to this competition and having a mobile app that actually helps us all. Thank you.
Thank you, Kamal.
Oh, by the way, I should have made some correction. I think Michael has been butchering my name. No, just kidding. It's Kamal. and it's very, not frequently, but there are times when people call me Camel, and I look nothing like it.
I'm sorry about that, Camel. Kamal. I've never been good with pronouncing names. And I think it's very true. I share the same experience, and Tom pointed out trial and error iteration. I think that's so important. I think that there are unrealistic expectations about data scientists being able to come up with some magic formula right off the bat that's going to be a game changer. It just doesn't work that way. And I think we need to change the expectations. Kamal, thank you very much. It was wonderful. I'd like to introduce a good friend of mine, Michelle Archuleta from Atlas. Thank you, Michelle.
Hello, everyone. So today I'm going to be talking about statistical interpretation of inherently structured data. So some of the talks we've seen so far have been looking at, like a small feature set, and now I'm going to dive into a very complex feature set. And my background, I got my doctorate in chemical engineering, and I've been doing bioinformatics and data science for the past 6-7 years. Okay, let's just begin with the nice problem. Let's consider balls. They can either be yellow or green, and they can either be flat or round. This is a nice problem for a lot of reasons. One is it's easy to interpret. So we inherently understand what color means. We inherently understand what roundness means. It's also nice because we have a lot of observations and few features. So we don't have to worry about overfitting a model. And then we don't expect there to be any correlations between color or roundness. So we can think of those variables as being independent. Okay, let's take a problem that's not so nice. Let's consider 20,000 features. And let's just say these are the names. They make no sense. We have no inherent sort of understanding of what these features are. And the other thing is we have a very small number of observations. And we don't know what relationships are between this feature set. So I pose the question, what relationships could be underlying the data? And I'm showing you a human embryonic stem cell. And now I slice it open. And these are pathways in human cancer. They're pathways that have been perturbed. And so the way in which the cell will respond to the body and its environment is it has a set of receptors on the cell membrane. And those receptors bind an external stimuli in the environment, and they produce a downstream effect of signals, of cascades, biochemical reactions. This leads to a particular protein going in and modifying our DNA. This then changes the entire system. How do we begin to understand this? So this was my challenge. I worked at Eisai pharmaceutical company. It's a Japanese pharmaceutical company in mid-sized pharma. So typically in biology, we do an experiment. We compare normal cells with maybe cancer cells, or maybe cancer cells with cells that are also cancerous, that they're receiving a drug or a treatment. And then is what we get back is a set of features. This can be genes, proteins, but this is an extremely long and complex feature set. And if we take this to the experts, to the immunologist, to the oncologist, and we say, hey, look at my nice list. I did this experiment, you know, what do you think? And they're gonna come back to us and they're gonna say, this makes no sense. You fail. So it's up to the data scientist to be the artist. You must provide the interpretable data. You must provide a context, meaning, what's the story? So instead of looking at all of these proteins, all of these genes, instead of considering that as our simple feature set, is what we want to do is we want to roll up the data. We want to roll up those pathways. And this is the idea behind a method that has been around for a long time in the bioinformatics community. And this method is known as pathway analysis. And so there's many commercial vendors that perform pathway analysis, and they use just very basic statistics. But if you read in the literature and you dive deeper, there's a lot more advanced statistical methods that are out there. These are really nice packages. They're available in R, all open source. And so there's been essentially 3 generations of pathway analysis tools. And my job was to go deeper. We don't want to just use what the commercial vendors are doing. We want to look at all of these unsolvable sort of based approaches and try to help us understand these complex diseases. So what the commercial vendors do is they look at overrepresentation analysis. This is essentially evaluating what fractions of features that came up as being different in our experiment, what fraction of those are in a pathway. And they're using just measurements such as the hypergeometrical and chi-squared binomial distributions. The limitation of this is that they're essentially saying that all of these features are independent of one another, which that's not true. And then they define sort of these arbitrary thresholds. Like, this feature is above, is significant because it's just above this threshold. So in cancer, if you look at cancer and you look at the landscape of cancer, is what you see are a few number of mountain genes. These are like the smoking guns. These are like, you know, they occur in many instances of cancer. But if you look at the vast majority of the landscape of cancer, it's made up of a bunch of hills, a bunch of rolling hills. These are genes or proteins that hide in the shadows. You know, sometimes individuals will have these mutations and it appears to be linked to cancer. So we're always just under that statistical threshold. So the hypothesis for the second generation of these methods is that although large changes in individual genes can be significant, weaker but coordinated changes can also be driving disease as well. And so one of the first papers that came out was titled, the method is gene set enrichment analysis. And with this method, instead of thinking of just looking at the overlap, this is thinking about it in terms of the distribution. So the way in which it's done is you first rank order your list of proteins that were features that were different between experiment A and experiment B, and then you calculate a running some statistic, and you say, where do those features lie within my pathway? And then you calculate a statistical null distribution so that you can come up with some statistics on how significant these particular pathways are. And you do this by, in this method, the approach they took was to permute the sample labels. So that's the way they did it. And the reason for doing it like that is you want to preserve the correlations within the feature list itself. So there's various methods that have come out around this, and they're improving on the fact they're looking at more multivariate methods for calculating the gene level statistic, and then they're also using different types of statistical methods for the pathway level analysis. And going back to how do you compute the statistical distribution, so there's two basic approaches. One is calculating sort of this competitive null, and that's where you're actually perturbing the feature set itself. But with that approach, you're disrupting the inherent correlation within the data. And then the preferred method that has really come out of the community is this self-contained null hypothesis. So with that, you're instead permuting the sample labels.
Can I ask a question just to be clear?
Sure.
You're talking about pathway. You're talking about a set of genes that are thought to be combination of cancer. Or is pathway something more general?
A pathway is well known, well defined. So it's, you know, in our cells we have biochemical reactions that occur under normal conditions. So that's essentially what a pathway is.
It's chemical pathway.
It's a chemical pathway, a biochemical.
Are pathways independent, or do they tend to have relations?
No, nothing's independent in this complex system. It's a hairball.
Awesome.
Okay, so getting into some more mathematics, this is just considering the fact that these genes or features, I'm trying not to use so much biology, but so these features within a pathway have relationships themselves. So it's using like this Hotelli T-squared statistic. And then, so there's benefits and limitations with this functional class scoring as well. The benefits are that it's not using this arbitrary threshold. It's beginning to take into account these correlations, but it's considering pathways to be independent of each other, and it's sort of discarding, you can have, like when you generate this ranked list, you can have features that have different magnitudes, but they occur, you know, close together on a ranked list, so it's disregarding those measurements. So the third generation of pathway analysis tools is trying to take into account the actual pathway structure. So the idea is we have all of this knowledge base, we have all of this understanding of how these biochemical reactions are occurring. So can we use that knowledge to sort of rank to help us discern, you know, the significance of these pathways. So it's also very similar. I'm not going to describe the slide too much, but it's very similar to the functional class scoring in that you have a gene level statistic, pathway level statistic, and the null distribution is calculated in a similar way. So this is actually getting into the signaling pathway impacts analysis is a type of pathway topology. It's a method. So here we're looking at, for example, here's two different pathway perturbations. So the grade node is a particular feature that is altered, and we can see that we get a smaller p-value statistic for this pathway because this node here is actually a bottleneck of the system. And so that's essentially what this method is doing. It's taking into account the topology.
Is it doing that through some kind of like graph theoretic approach where you're looking at, you know, the interconnect? I mean, since they're all are interconnected, it seems like you could represent it as a network and compute the normal.
Yeah, it's what they're doing here is they're calculating the null hypothesis based on just randomly doing perturbations of the nodes. So you have two nodes that are perturbed. You're going to randomly perturb all combinations in that network to generate your null distribution, and then you're going to compare that with your actual data, and then that's going to tell you whether this pathway topology is really statistically significant. And so the limitations or the benefits of this is that now we're actually diving into we're trying to leverage the knowledge and trying to get into the pathway topology. So, you know, as if this isn't complicated enough, the other thing we need to think about is cell types. So different cells make different levels of proteins, so that's going to alter the pathway topology. So we have to have knowledge of also too the cell type information to be able to better develop these models. And these are sort of evaluating a static state of the system. And so, you know, there's a lot of outstanding challenges in the field. One thing that I didn't really touch on that much, I went into more of the statistics, but that is the annotation. So there's these knowledge bases that are out there. Some of these have like low resolution, and they have incomplete and inaccurate annotations, and then they're not very specific for cell types. What I was doing is looking at trying to use an ensemble of all these approaches to look at sort of the data and what makes sense and what comes with the data. But there's no real benchmark of these methods. And it's actually very hard to benchmark these methods. And then they're not capturing the dynamics of the cell, and they're not capturing external stimuli. This is fake data as well, because I can't show real data. And this is like a picture of different pathways, and the red represents those that are upregulated, and the blue represents those that are downregulated. But so this gives you sort of an idea of you know, what the output is of these methods. And then my concluding slide is this, that if we take a step back and think about what we're doing, and think about this as sort of like a galaxy. So the first generation approaches are just picking out the bright stars in the solar system. Those are, you know, the smoking guns, and those methods, they're picking up on that. The functional class scoring methods are picking up on sort of coordinated changes that are just, you know, below the surface. That's what they're picking up on. And then the pathway topology is really, you know, dependent on the knowledge base, and you know, so you're getting different pictures of the data. And we don't know where the biomarker is going to lie. What is a biomarker? A biomarker is a feature that's going to tell us whether a patient is going to respond to a drug, whether therapy is going to work and be effective. One of the things that you have to do as a data scientist is you have to be able to convince, domain experts, like, why is this valuable? And I tell biologists this, that do you believe that there's a single experiment that you can do that will help you understand the entire, cell? And they, laugh. No, you can't do that. So I tell them the same thing. Like, we cannot just look at this data from one lens. We have to look at it from many lenses. And so, thank you.
So since in our terminology it's called the data scientist, and scientists tend to make design of experiments and study design and all that, as you approach the problem, and actually I think about it more generally, what I've heard everything I've heard tonight is, well, we just fiddle a lot of dials and see what happens. But where in the moniker scientist do you, in this rocket science, do you act like a scientist? Do you make a hypothesis? Do you make a design of experiments? Or if we're talking about productization, certainly you don't just make a product, throw it out in the market, hope people will buy it. There is a hypothesis that has to go into the market. So we've been trying to define a little bit of what data scientist is, and it occurred to me I've never heard that said ever in the context of data science. So I haven't heard it. Do you approach it that way?
So, I would have to work alongside immunologists and oncologists, and I would have to, help them with their hypothesis. They have this idea that, these pathways, blah, 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 and, I have to come in and be objective, and also I have to have a lot of domain expertise in this area as well, so that, so that I can effectively communicate with them. And so I have to, it's really a partnership, I would say.
So, this might be a little bit of a complex question. So, imagine if I said, okay, forget biology. I'm going to give you a full little race car, and as it's driving down the track, I'm going to put every sensor, every piece of component, so you have endless amount of telemetry. And all I want you to do is answer two questions. Can you tell me at any time what your assessment is about diagnostically about how that race car is doing from the health status? And can you make predictions about how it's going to be impacted by weather, things like that? But I'm assuming you know nothing about hearts. So now because you're looking at basic sensitivity between stimulus versus responses, knowing that these pathways are there. And now give you a system of systems that has completely different pathways. Would this model break down, or would you be able to learn those new pathways and relationships between features?
I think this approach and these methods are sort of a little bit more exploratory than, predictive modeling, because it's really built on this domain knowledge. So like I talked about, the second and third generation methods, those would probably be out. We'd be probably talking about just like the simple overlap analysis. For that, it should work, it should, but when you have we're trying to build in, all of the domain knowledge, so that's.
So is the domain knowledge in this problem, because it's not entirely clear what the domain knowledge is it in reducing the size of your space or your relative parameters?
So let's just.
In which case the race car.
Yeah.
Should have to know exactly which piece.
That's what I'm getting to. Yeah. Would it be able to determine whether the machine have to know in advance with an automotive engineer? This is going to call you in and be able to get that cost that in advance.
Is there analysis?
Yeah.
So I mean, domain knowledge is this, like, you know.
Oh, I see that exists. I'm wondering how this diagram helps you run the analysis. And I know it's a complex question. I don't know about that.
Yeah. Let me step back for a minute because, I mean, this is not the only sort of area that I've done in this space. So I've definitely used, you know, much like predictive modeling and you know, these type of things to look at this because, yeah, most definitely you can, you know, yeah, I mean, is what, you know, going back to like, I guess my galaxy thing, which you're essentially zooming in on a particular pathway and using the domain knowledge of the architecture to rank those pathways. So I hope I cleared that up. Yeah. Okay. I'm sorry. I don't know who was.
I'm not sure if Hail Mary is new here, but what it sounds like they're getting at a little bit, and what your problem might be using this approach is just your sample size. So you have thousands on millions of pathways you can look at and build out like a p-value of 15 and say, hey, we at least can rank this pathway and look at it because we don't have a lower p-value. Whereas with the race car, you don't have enough connections to build anything above, you know, p is 50. What the heck does that mean? So if you had thousands of race cars, then perhaps you could use something like this if you rank the connections. That was actually
Yeah, so that's, you know,
it's not so much domain as sample size, although it's really both in this case.
Yeah, it is. Yeah, because, you know, in this system, you're totally at the other end of the spectrum in terms of like, you have this enormous feature set, and, you know, I mean, they're coming out with amazing technologies and everything all the time, but you're always going to have very, you know, small observations. So you're always, like, over-prediction is always there and always relevant.
I think the future of this kind of research is saying we were able to add that dynamic aspect.
So actually, going back to my graduate work, I did that, and I came from, you know, like more of the mathematics, like my doctorate work was more of like applied mathematics, and I modeled these signaling pathways, and I was very attached to that. And it took me a while to get into data science and be like, here's the data, because I wanted to understand them and have mathematical models for all the relationships. So, and come at it like several different approaches. I think you had a question.
I was just curious, when you got to the point of the biomarker, is that like, you know, sort of, to put it in lay person's terms, is that when you come out and say, you've got 2 generations of breast cancer, then you're going to have breast cancer? They don't say that.
Yeah, it's,
you know, that some of all of these factors can play a role, and you don't know what to make of it.
Yeah, it's extremely complex. So what we were looking at specifically in terms of like the biomarkers was patients are all different. All of our, you know, genetics are different. And that's why it's such a hard problem. It is so hard to develop a therapy. And biomarkers are huge in the pharmaceutical space because pharma has taken so many drugs to phase 3 clinical trials, and they just fall apart because we're recruiting the wrong patients in. They don't have the right genetic background. And I mean, it was really sad. In 2014, there were several, supposed to be blockbuster drugs for Alzheimer's disease. They were in phase 3 clinical trials, and I think Pfizer, Eli Lilly, just boom, 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 failures. Really sad. And looking back at the data, the reason is they were recruiting like patients into their clinical trials that had that they were too far along in Alzheimer's, and it's believed that they need to recruit patients that at early onset of the disease. So that's why this is so important.
So the big difference between a human cell and a Formula One or an Indy car is that humans design and build an Indy car. That's not true of a human cell. So if I'm hearing you correctly, there's a lot that we don't understand about the human cell. We don't really know its blueprint. It's more like we know it in terms of a sketch. And then all more so when it comes to analyzing malfunction of a human cell, that is human cancer, right? And all the variations that come with that. So if I understand what you were saying, there's a lot of things that we don't know. But there are some things that we think we know. So how do you, I mean, you're just trying to sit down and describe this to a high school, right? About the data that you do have, and then how you perform as a scientist, and then how you use predictive modeling to learn and apply machine learning in this work. How would you like just have a 2-minute explanation of that to like someone at a high school level? I mean, I'm thinking of Einstein here, where, you know, theoretical physics, he said things, well, we want to simplify, but we can only simplify it so far, something like theoretical physics. And that's kind of what I'm just trying to grasp this. I actually have cancer myself. I've been dealing with cancer for 6 years. So this is kind of a subject that's interesting to me. And one thing that I've learned is that there's a lot we don't know. But you know some things. How do you take those 2 or 3 big major steps and apply data science and machine learning to this work?
You have to do it, and you have to do it like aggressively, and that's what we do. Like, we have to try many different things, many different ways. So there's the knowledge base, and we can use that. So we can use our knowledge and try to build algorithms and predictions based on the knowledge. Then we can take the more of the machine learning, just look at the data, pull out interesting signals, and go with that. And so it's all over the place. We're going to apply as many tools as we can to this, but ultimately there's no tool that gives you the right answer. So it's the same thing, and that goes back to the same thing, that we have to apply many different statistical lenses, many different algorithmic lenses to understand this extremely complex biology. Because in my opinion, there's never going to be a single method that's going to predict everything. I don't know, maybe IBM disagrees.
The answer is that the cost of compute power storage has come down significantly, and we're getting better and better data, collecting more data, and we need to innovate and create new techniques. So it reminds me, Michelle said that a data scientist is an artist, and I think that's very true. A lot of people think it's just pure math and science. I'll tell you a story. I was in a meeting the other day with 6 data scientists, very high level, and we presented them with the same data set and evidence. And guess what? They came up with 6 different interpretations of the evidence. And there was no right or wrong. They just had a different interpretation. So a lot of it does have to do with interpretation. We need to be careful about people saying, oh, the data just speaks for itself. I'm sorry, the data just doesn't speak for itself. Usually the data has been collected by humans. Humans are flawed, we're biased, and we need to be very, very careful. And I think a good data scientist is always skeptical, even of your own work. You should always be especially skeptical of your own work. Anyway, thank you, Michelle. Thank you all for staying. We have 2 more. I'd like to introduce my good friend, Nancy Abramson. Thank you, Nancy.
Thank you.
a lot tonight, and so don't you think? Can we just give another round of applause for people who have already presented today? I am more of an artist than a statistician after following Michelle. I'll make that clear. Thank you. Thank you. I'm Abramson. I'm a product data scientist, and as many are like here tonight, I have scrubbed my data so it's not recognizable. So I'm a subcontractor for a telecommunications company. Here we go. And we create applications that run on websites. And we have problems with applications crashing. And the area of the company that I'm working with has to do with the health of, I monitor the health of our applications and of our systems and our hardware out in the field. So the application crashes. We don't know how to test for it. We've tried to replicate it. We're unsuccessful. Can't replicate it. Even if the programmers do fix bugs, we don't know if they're fixing the correct ones. And our customers are having poor experiences because they use our applications and they're not working. So, easy problem. I think that this is, I can do some data. What was it? Data product with this. So, the way I'm going to present my data, and I just want to echo what other people have said today, is that you can go and you can analyze data and you can see things, and I often do see things, and I go to show my business user or my executive, and they just look at me like, what's the point? So it's so powerful to be able to display your information elegantly. And what I really enjoy using are what is called a Sankey diagram. And a Sankey diagram is much like a map. This is a map of the London Underground subway system. And it just shows how, much like a map, this map is showing how the subway flows from subway station to subway station. This is an actual Sankey diagram. It's often used for power and flow. That's where its history is derived from. It's flowing points, like I said, from one event to another. This is, as you can see, just types of energy, how energy is wasted in the percentages. But what I want to point here is, first of all, you see this yellow flows up here, and some of it is applied energy, and some of it is wasted. But this is a very, what I call information-dense diagram. You're giving sheets and sheets and sheets of information to a user who can visually understand it, because we understand visuals a lot. We can process a lot of information with our eyes. So this whole system, as you can see, the steam is I guess the fuel is the biggest one, and then you can see the gray areas where waste is. So I have shown these diagrams to executives, to developers, to testers, and it's like this universal way to present information that's easily understood. The analysis I did is a data type analysis, in that I combined semi-structured data to semi-structured data analysis using SQL tools. I didn't use Python or R or anything like that. What I did use was a tool called Teradata Aster, which is a SQL-based analytics tool that sits on top of Hadoop. So it looks a little like MapReduce, if anyone here is familiar with MapReduce. So what I'm going to present are the best practices to blend these multiple data sources and some of the sticky points that you may come up. in order to show the final diagram of all the data collapse. And the application can be automated. You can actually embed this inside of your code and have a redirection of your user. If you suspect that path will produce an error, you can take them off to a save page. And interestingly enough, I was taken to a save page today when I clicked on LinkedIn. It said LinkedIn is, I got a page that showed LinkedIn is processing something, but it wasn't a catastrophic error. I didn't like lose my entire web page. The two data sources that I'm bringing together are very common in the web world and common certainly in the Linux world. If you've been in Linux at all, you're probably familiar with the Apache log. And Apache log is our developers write our code using Java, and we'll actually write to the using Tomcat to go to the log. It's a semi-structured, as I mentioned. It's also event-driven, which looks a lot different than your normal database structure or some of the other types of data we've been speaking about tonight. And what I mean by event data, each of these, both Adobe gives event data and Apache gives event data, is that we have something happen, it gets recorded. I like to explain it as frames in a film. So you take a snapshot in time, and that's what's going on. You take another snapshot in time and write it down and keep on going. And that's how actually both Apache and Omniture record data. Omniture records website behavioral data. Apache records all kinds of things going on in your system. The bulk of my work was spent on purely the data side. This is where all my heavy lifting went, because I was taking data sources from actually different countries where the servers were located. So we outsourced our data providers. And even if we hadn't outsourced our data providers, many of you familiar with databases are familiar with surrogate keys, which each application will generate its own surrogate key, which is just an identifier of the event in the row. It's only meaningful for that domain, only for its own domain. Our third-party tools also have their own session definition. So they have what they call from when the event starts and goes through a bunch of processes, and what it calls when the event ends is called a session, much like what we consider a session if we log into a computer, do a bunch of work, and log out. They also have data elements, which is what we want, right? We want to see why blend data in the first place. We want to see the different angles of the data. We want to be able to twist the data around to get the different perspectives on what's happening with the user. In order to harmonize this data, there's some very easy things you can do, and these are just best practices that are hopefully already in place. If not, there are good system administration practices such as network time protocol, having all your servers synced. So if you have a server sync in Russia, it's going to give you the same time as your server synced in Texas. Also, to store timestamps without a time zone so that you're able to add and subtract times across your different servers, across the different geos. I see some people shaking their heads like they've perhaps gone down this road as well. And the different data sources, to combine them into conformed columns, even though they may have different definitions, they may functionally act the same, but just giving you different types of insight according to the data source. Again, another metadata best practice is to list where your data is coming from. Is it coming from Adobe? Is it coming from the Tomcat log, the insert date timestamp, and work with your business on what the business thinks a business definition is, a session is. Is it when the user logs in, does things, what happens when the user perhaps logs in, goes out for lunch, and the system is idle for, an hour? Do you count that as part of the session, or do you have a timeout? Those are really business questions. They're not, a smart data scientist will ask those questions, but they can't come up with answers without working with the business. And in order to create a session, and again, I'm using SQL, so these are SQL terms for those of you familiar with databases, is I create a partial window over a natural key. So before I had mentioned that oftentimes your data sources have what's called a surrogate key, or artificially opposed counter. It's just sitting there counting, saying here's row 1, here's row 2, here's row 3. Well, that doesn't mean anything to another data source. It may have its own rows 1 or 2 or 3 with completely different users. A natural key is just something like it sounds like. It's a key that happens in nature, like a user ID, an account number, an email address that identifies the instance that you want to do the analysis on. And then from there, you bring in your natural key, and then you order by time. That way you have a nice well-behaved time. And then from there, you use your business rules to decide the session and select what types of values you want to look at through the window, because the goal, again, is to make this data very information dense, to make it very dense. So we're going to be aggregating the data together, as I'll show in a few slides. And also, as I keep mentioning, these are event-driven data. So when Adobe goes onto a web page, and you go onto, say you go to your account page. Say you go to your account page, it puts, it creates an event, and on page name it puts your account, but button click and title name are both blank. And then you say, okay, I'm done with page name, I'm going to close that page. You click the button close, and the next event has a new timestamp, and has button click, the page name and title name are both empty. So this generates a sparse data set. But I can call it behavior by coalescing this data together. And also, what I did find out in this data is that I had user IDs were not always recorded. For some reason, I would get occasional nulls. So I couldn't randomly pull out my user ID from the session. I had to look at perhaps the event above it or below it, and then use that user ID. And that's what this SQL is. I thought some people might be interested in seeing some SQL that was written to help clean up the data. This is even more complex, and this is where, working with business and knowing the domain, I can find out, even though, let's see, so if I have an event is null, or the event's like app, and the channel ID is null, then I'm going to go with a column called error code, and that all becomes my flick. And you can see these are a bunch of very complex rules, but again, having seen the data, it's all very sparse, and this was a business way of going through the data and systematically compressing that data so that we have a rich column called clip that has as much data in it as possible. So this is where I'm trying to get to in leading up with all the data cleansing and session IDs, in that I have my natural key. This would be my natural key because it shows up in both of my data sources of Omiger and Tomcat. And here I have a simplified view of the table with the events. And I'm interested, I'm only pulling in records with error codes, because that's what I'm interested in to improve the user experience. So what I'm showing here is this ID that starts with, I should say, ends with 39Q. These are all the events in its session, and by aggregating or collapsing them, I end up with one error code, which is how I define my session. I'm only going to have one error code. And I have my natural key or common ID. But what I end up with is this event stream called your account message close. And what happens is, because this is sorted by time, this is where it gets really exciting, is that you have time sorted here. So what you're seeing is what happens the previous 3 events before the user error is out. Okay. So these rows compress to these 3 rows, and I have my events here. And what I'm going to do is, in this summary table, I will count how many times each of these series occurs, and those will be in common paths. So on the event row compression, I really wanted to show how we're displaying an enormous amount of data, just an enormous amount of data, because I have over 1 million Adobe rows coming in. I have over 4 million Apache rows coming into the system. I aggregate them together into those events that I showed on the previous slide, and then that will then produce my Sankey diagram of about a dozen events, and that will be able to display right there. So this is the resulting Sankey diagram, and what's really nice about this is that I was able to go to developers and say that the common path was for someone to click close, then go to their account, click close again, and then you get a multitude of error conditions. So then the developers were able to be more focused on where they looked in their code to see if there were any issues, and testing was able to replicate this. I haven't gotten to the automatic part, but ideally you would have this baked into your code so that if any certain path started bubbling up lots of errors, that you could report, give out an alert, and also reroute before you had a catastrophic unintentional failure for the user. I also want to say that there's an overwhelming amount of information available on the internet, and a lot of what's being used today has been around for a while, like in the past 50 or 100 years, even the statistical methods. Many of them are not that recent. So if you have a solid foundation in statistics, and Coursera has excellent classes, Galvanize also has excellent classes, and the Edward Tufte has a really nice book, if you haven't heard of him, in his series of books on how to display data efficiently for people to understand. And what's really nice is you can apply that to Microsoft Excel, you can apply that to Tableau, you can apply that to a Python display. It's just a foundation of understanding how people process information. So that's all I have. If there's it's late.
Your Sankey diagram, what tool did you use to produce that one?
Oh, I apologize. I meant to mention that. Thank you very much. The stack I used for this was Teradata Aster, and this is out of their graphing tool called App Center. And it's an enterprise tool. It's not open source. Yes.
You can also use D3.
Quick question. You had a ton of SQL in there. A lot of people in the cutting edge seem to have a deep preference for no SQL. As someone who's working in it, where you see it going, is no SQL eventually going to take over, or how long will that take?
You know, NoSQL is a funny name, I think, because Teradata is on Aster Teradata is actually on the Hadoop stack, and we also have a Hive interface with a NoSQL. Well, NoSQL, the syntax, it's still structured data, and the syntax looks very ANSI SQL-like.
So NoSQL is just better SQL?
Yeah. It's on a Hadoop Platte. Well, there's lots of NoSQL. I mean, there's Cassandra and MongoDB and that sort of thing. I'm familiar with Hive, and I know that it looks a lot like the SQL I know. Any other question?
Hive is actually providing a really SQL-like into databases. So this is a classic problem.
Hive was the question.
Well, that's not really a question.
Oh, okay. No, I think I may have lost that.
The reason why Hive looks familiar is because they're actually putting the SQL interface upstream of a which stands up in the middle. People have said like not having SQL.
I knew that there was some other, but it comes out like no SQL. But really, it has some SQL-like extensions. You're right. Hive has just wonderful windowing functionality and analytics, which is very powerful. So
you definitely not only can Cassandra these things, like SQL, so your records are not huge. Cassandra can do a lot more. Cassandra.
Yeah, and it's free, right? Yeah.
That's what it is.
Hey, I think you're next. I think. the battery's gone.
Is the battery in? Is this thing on? Okay, hello, testing, 1, 2, 3, 4. Testing 1, 2, 3, 4. Okay, I think the microphone's out. Can you all hear me?
Yeah.
All right, I'll try and speak up a bit. I'm Michael Walker with the Data Science Association, and this is all part of a big machine learning contest that we're holding, and I want to shout out some names. First of all, my partner over at the Data Science Association, Michael Malik. Everybody give a hand to Michael, because a lot of you see me and you can hear me, and Mike's sort of in the background, but to tell you the truth, the real secret sauce is Michael Malik. He's responsible for a lot of the success. I couldn't do this without him, so thank you, Michael. He's a great professional. He's one of the few people who knows data engineering and data science. He's sort of a polymath, and he's turned into a great friend, and I'd really be lost without him. Also, Tom Flaherty. Thank you, Tom. Tom's another guy who's just brilliant, and he's really helped clarify my thinking on some things. So thank you so much, Tom. And I really rely on him. I bounce a lot of ideas off of Tom, and I can always rely on Tom to have a unique point of view, but also a clarity of thought about what I'm trying to do that really helps me put it into perspective and adds a lot of value. Also, our friends at Galvanize, Jared and Dan and Mike, thank you guys. They're wonderful people. You really need to check out their data science program. It's really fantastic. And we're really lucky that we have you guys involved with us. Thank you so much. My partner who's not here today, he was sick. His name's Paul Ballas. He runs the LinkedIn Big Data Group, and I couldn't do this without Paul. He's a great guy who's really a good friend, and we're missing him today, but he'll be back, I think, next time. So I also, we're going to need some help at the machine learning contest, which I think we're having another symposium next month. I think it's going to be about October 14th. We're going to need some help setting that up, and then our award ceremony and party, which will be at level 3 on December 5th. So if anybody wants to volunteer and help us out, you're going to meet some wonderful people like Tom and Paul and Chris Howard and other people. We'd love to have you. You're going to learn a lot. You're going to get access to the latest machine learning techniques. You'll expand your professional network. So please, if you'd like to get involved, please talk to me or my partner, Paul. This is my day job at Rose Business Technologies, and I'm going to talk a little bit about the business application of machine learning and about some of the things that we're doing. I'm really excited because it's in its infancy. We're really just starting. But I'm so excited because it adds a lot of high value. And when you talk about data science, often you're talking about 3 areas of analytics: descriptive, predictive, and prescriptive. We're just learning how to do predictive, and we're just barely scraping the prescriptive, and I think machine learning is now helping bridge predictive and prescriptive. So here's my definition, and this is really more of an application definition than it is a technical definition. It's continuously, keyword continuously, adding new data to improve and modify a set of algorithms in processes that continuously inform and improve functional capabilities. Again, functional capabilities. That means in any organization, your machine learning algorithms have to add value, whether it's to the decision makers on the strategic level, on the tactical level, or the operational level. So this is something that was done by my friend Steve. It's a skills pyramid. It's about a year old, and I think it's a useful way to look at the different categories of data engineer, machine learning researcher. What we're finding at Rose is that the data scientists really need to combine machine learning engineer and researcher. So this is basically blurring together, and the data scientists really need to be able to design, architect the algorithms as well as execute them, and be able to work in teams, because you're going to need people with specialized domain expertise to be able to help you. So what are the domains? Well, the top ones are finance, retail, marketing, healthcare, e-commerce, human resources. This is today. This is today. In the future, I think it's going to be very important in the legal system, in national security, and all sorts of security areas. In government, I mean, our government today is not sustainable. It's just not efficiently providing us with enough services for our dollar. And I think that data science and machine learning has at least the potential to help with efficiencies. And of course, manufacturing, designing products, and the Internet of Things. So what are the applications? Right now, the most important one, or at least the one that we're working with that has the most value, is dynamic pricing capabilities. In the near future, it's already starting at some levels, especially in healthcare and in engineering, is decision support systems. Predicting market trends, predicting customer needs, hiring people, human capital management, risk management, supply chain. These are all things that we're just starting to apply machine learning algorithms to. Fraud detection, that's been around for a while, but we're actually using machine learning to become even more sophisticated about fraud detection. Collection analysis, cross-selling, economic forecasting is still an area rife with problems because it's a high causal density environment, meaning there are a lot of different causes in the economy. But I can assure you we are getting better, and as we improve our machine learning algorithms, as we get more powerful compute power, as we get higher quality data, I think in the future we're just going to get better and better with our predictions. Will we ever be able to predict perfectly? Absolutely not. But if we can get better with our predictions, we can plan better and have better policy and better responses to the economic situation. So right now, I'm going to talk about 5 different machine learning applications that are happening right now and that add significant value. So business, dynamic pricing capabilities, healthcare, finance, marketing, and decision support systems. So dynamic pricing capabilities. You remember about 10 years ago when you would get on a flight, it would be hit or miss. Either the flight would be totally full, or it may be half empty, or maybe significantly empty. And today, you almost never get on a flight with any empty seats, right? Well, why is that? It's because the airlines are employing very sophisticated dynamic pricing algorithms, and they're looking at supply and demand. They're feeding data into the machine learning algorithms about what's happened in the past, and they're adjusting their prices and who they're marketing the seats to. Same thing with a lot of different areas in the hotel industry, hotels. So during a conference, when there's high demand, they will raise the rates. When there isn't a conference, or where historically there's been low demand, they'll lower the rates and then send out coupons for discounts in order to fill the hotel up. And this is just price optimization. It's making sure that you can use your app, you can optimize the monetization of your assets. So the classic example is Airbnb. I'm just curious, how many people have used Airbnb? It's wonderful. I mean, I will suggest to you that Airbnb is really a data science and machine learning company. So what is this? This is a map of all the different properties in Airbnb, and they basically do 2 things. One, they look at historical data of supply and demand so they can price it right to optimize a certain property getting rented out. The second thing they do is they collect the data to find out what humans are actually looking at and how they make their decisions on what properties they find attractive to rent. And they found all sorts of incredible things. And just one is the experts told Airbnb people are more likely to rent out a property if you have a picture of a beautiful, glossy picture of the outside of the property. It turns out when they ran the experiments, it's not true. What's true is people care more about the inside. So if you have a few general pictures of the inside, that actually sells the property more. Well, this is really important information. Again, what is real data science about? It's about finding truths that few other people know that adds value. That adds incredible value. Dynamic pricing capabilities. By the way, Airbnb developed and basically designed a machine learning algorithm that specializes in dynamic pricing capabilities called Aerosol. Last week they open sourced it, so any of you can go to the Aerosol site. I think we posted a link to it at the Data Science Association site, and you can download it and start messing around with it. You can actually apply it to many different areas and see how this works. It's incredibly valuable. So here you can see during a music festival, during high demand times, that's when you're going to raise the prices. But in other times when there's low demand, you lower the prices so that you can optimize the monetization of your asset. What is Lyft and Uber? How many people have used Lyft or Uber? A lot of people. I think the majority of people. They're great. What are they? They're data science machine learning companies. It's all run on machine learning. So Uber has a set of machine learning algorithms that determines how many drivers they need in a specific area. It determines the price of a ride from point A to point B. And it's not set. They're collecting new data, feeding it into their machine learning algorithms, and adjusting every day. It's learning. The machines are learning every day to better optimize their pricing strategy and their, I guess, what would you call it? Supply chain demand, right? You know, how many drivers do you need actually on the street in a certain, you know, in Lodo, in Denver, you know, or in the Village in New York City. So you look at the past data and say, you know, okay, in the first 2 weeks of September, for the last 3 years, you know, here's the data, and you're collecting new data which changes that. So again, it's continuously adding new data that improves your functional capabilities. Walmart. Well, we all know Walmart innovated supply chain management. Now, Walmart is using machine learning algorithms to better set prices of their goods so that they'll move off of the shelf quicker so they can sell more goods and resupply their stores. Healthcare. We all know that healthcare is inefficient and is ripe for major disruption and innovation, and machine learning algorithms are just starting. It's in its infancy, and we need more people like Michelle and more people like you to really get into this, who are very creative and will start experimenting in this area. So United Health Group and other insurance companies are just starting to employ machine learning algorithms in a number of different areas. They're collecting data about their members, about humans that are part of their group, to better predict what kind of healthcare and the cost you know, that they will need, and perhaps some preemptive plans about how they could suggest to people how they can have a more active, healthy lifestyle. So I'm going to talk very quickly about 3 new startups, because I think a lot of healthcare is there are a lot of forces that favor the status quo. So you're really going to need startups that are going to disrupt. And this is one, I think it's pronounced Lumiera. They just raised $10 million in venture capital, and they use probability theory as well as collecting a lot of data about people, and then suggest to insurance companies, hospitals, and individual physicians I guess, what would you call it, the healthcare optimization for the individual. Analytic is a fantastic new startup that just raised $5 million in venture capital, and they're assisting hospitals and physicians with diagnostics. Again, they're collecting a whole bunch of different data, running it through machine learning algorithms, continuing, again, to collect the data to make recommendations on the optimal care for people. I think this has incredible potential. And I think if you really stop to think about it, this is going to radically change the practice of medicine. I mean, the physicians today are not being trained in any of this. My prediction is that this new way of looking at healthcare will outperform the old medical practice. So you're going to see a lot of disruption in the next, I don't know, 15, 20 years. PhysIQ works with body sensors. I love this idea. I think they just raised, what, about $4 million in venture capital. I predict that in 3 to 5 years, we're all going to be putting little sensors into our body that's going to be transmitting data. And companies like PhysIQ are going to be doing the analytics on it, and again, helping to optimize our healthcare with ourselves involved, and maybe traditional physicians involved, but I think it's going to radically change, and I predict that the cost of healthcare will go down. The trade-off is I think each individual, including all of us, are going to need to be more responsible about understanding our own bodies, our own health, because my program and what's optimal for me is going to be very different than what's optimal for Michelle, or what's optimal for Michael or Tom. And so it's going to become very personalized. And the only way we can do that is to collect as much data as possible. Finance. The leader here of the big investment banks are Goldman Sachs. And Goldman Sachs has been using data analytics, for 50 years, and in the last couple of years has been experimenting with different machine learning techniques, and it's working. Goldman Sachs outperforms almost every other investment bank, and the reason why is data science and machine learning algorithms. So I want to tell you about 2 hedge funds. Now, most hedge funds are not worth investing in. You're better off investing in index funds, just statistically. I mean, this is evidence, from the data. But I'm going to tell you about 2 that do outperform the market. One is Renaissance Technologies, and the guy who runs that is a scientist. His name's James Simons. He's a former professor, I think, at the University of, I think it's New York University at Stony Brook. So he decided that he didn't want to be a professor anymore about 20 years ago. And he started to develop theories of different data science techniques and started building high-performance computing systems, and hired basically data scientists. And it worked amazingly well. These guys have outperformed their own industry for 20 years. And in the last couple years, they've been experimenting with high-performance computing and machine learning algorithms, and have done amazing things. They've predicted accurately market trends. They've put together different data or financial products that they can trade on. They've designed and executed certain trades that have outperformed almost everybody. And if you ever went and visited them, you'd think that they were all a bunch of nerds and data scientists and professors, because they're all scientists and they're all using data and sitting around basically coming up with theories and then designing trades around their theories. So you'd be, it's not like the Wall Street movies, where they're testosterone, hustle and bustle and yelling and all that stuff. They're very calm. It's almost like an academic conference room. It's really interesting. The other is 2 Sigma. And 2 Sigma is probably leading in developing machine learning algorithms, again, for predicting markets and being able to test theory. So a lot of what we want to do in finance is you want to come up with a theory. And the only way to make money, real money, as a trader, is to know something that very few or no one else knows. So I may have a theory that professional football, the NFL, is peaking, and it's going to go down in the next few years. And I want to design a trade around that. How do I, do that? I have to use computers, I have to use data, and I need to use some sort of Monte Carlo simulations to try and test out my theories before my partners are going to allow me to place, millions of dollars of bets on something like that. So that's the process that they use. Marketing, this is huge. You know about retail, everybody knows about A/B testing. A/B testing done well adds an enormous amount of value, but now machine learning algorithms with recommendation engines are changing the ballgame. They're improving all the time. Predictions, retail fraud, again, price optimization, supply chain forecasting, location analytics, all this is revolutionizing retail. So Walmart, again, is leading in this area. They are using machine learning algorithms to optimize their supply chain, predicting consumer trends. I give you an example. Let's say they found, and this is very odd, no one knows why, if a hurricane is about to hit an area, people load up on Pop-Tarts. So if they find out a hurricane's going to hit, let's say in Miami, and they've got a bunch of Walmart stores in Miami, they will ship as much Pop-Tarts as they possibly can. So stuff like that makes a huge difference. Amazon, well, we all know about Amazon. They use their recommendation engine, which is pretty good, and I think it's getting better and better, as well as their supply chain optimization. Facebook. So Facebook is using sophisticated machine learning algorithms to target specific advertising to people who are more likely than not to click on that advertising or be interested in this type of product. And then they're looking at the different relationships that people have on Facebook and then targeting them. And they're starting to do pretty well doing it. Apparently the advertising is working better than other traditional advertising. So I think they have a promising future. Again, using a machine learning algorithm data science strategy. LinkedIn, the same thing. They're finding out what the relationships are. So they find out by maybe trial and error showing Mike Malik a laptop advertisement, and Mike buys it, and then Tom is in Mike's circle, a relationship friendly with him on LinkedIn as Michelle is, and so they will target ads to Tom and Michelle because they are more likely than other people here to buy that laptop. Again, machine learning techniques take all this data, use scientific methods, and optimize the personalization, specialization of advertising. And we're just beginning in this area. Guild, I think, is another one, an e-commerce site that is using machine learning algorithms to specifically target certain products at certain people based on their usage. Ford uses this. Ford's actually one of the leaders in data science. They do it basically two ways. One, they are looking at consumer trends. So how many red Mustangs should we build? How many black Mustangs? So to try to predict how many black Ford F-150 trucks we should build. This is really important on the supply side. It can save them, it has saved them, not only millions, but I think billions of dollars. And then they're also embedding sensors into the engines to do predictive maintenance. So using highly specialized anomaly detection algorithms, they are able to detect strange things going on in the engine, alert the driver, come in, that has amazing value, especially, and will cause more people to buy Fords, because obviously your Ford will last a whole lot longer if you have predictive maintenance. Target is using it more and more, again, trying to predict consumer trends, trying to understand maybe more women are buying lipstick. They don't even need to know why. They just need to know this is a trend and we need to stock up on more lipstick, and we need to send more promotions to different women who are likely to buy that lipstick. So decision support systems, and I've been involved with this pretty seriously now for about a year, and I think that this is going to revolutionize business and government. So Google is one of the leaders in decision support systems. Google has so much data to play around with. And for decision support systems to work, you really need a lot of high quality data. And you need to understand the different processes and how to augment human intelligence. And it sounds easy, it's actually very, very difficult to pull off correctly. But again, once you pull this off correctly, as Google has figured out how to do, and now we're figuring out how to apply it to specific organizations, you have a tremendous competitive advantage. Netflix, they basically do it in two ways. One, how many have Netflix? I have Netflix, and do you ever go up on that top menu and say, because you watch this, we recommend you watch this? Well, I do this too, and it's actually pretty good. They actually show me things that I'm more interested in than other things, and I'm amazed. But they're also now, I don't know if you've noticed this, they're saying, well, because somebody else that you know watched this, we recommend you watch this. And I thought, wow, how are they doing that? Well, through machine learning algorithms. It's done an amazing thing for Netflix business, and I think it's pretty good. It's pretty accurate. Second thing they're doing is, and this blows my mind, and I don't know if this is going to work long term, but it's working now. How many people watch House of Cards? I love that show, right? But they use sophisticated algorithms to help them develop the plot. So they're using machine learning algorithms to try to predict what type of plots, what type of scenarios people are going to enjoy watching based upon the ratings of what they watched in the past.
All right, so I've been thinking about this. How long do you think it's going to be before they actually start doing choose your own adventure type programs to the point where, depending on who you are, you might actually see more customized program?
A few years.
Yeah, I mean,
exactly right. So I don't even know how to think about this, and it blows my mind. But it's working because I love House of Cards, and I don't know how many of you like it too, but my wife likes it, and my kids like it, so they're doing something right. How they do it, I really don't know. But they're doing it, and there's probably a dark side to this. I mean, I haven't really thought that deep about it, but it's manipulation at some level. And as long as it's harmless manipulation, it's pure entertainment, it's probably okay, right? But once it starts harming, and I'm sure we can think of several scenarios where it can, we're going to have some big problems, especially maybe politicians in society starting to manipulate us. The military. The military has been using it for years and years and years. Actually, the military has been using machine learning probably starting about 10 years ago. I think they're about 10 years ahead of the private sector. But you won't know about it because most of the stuff is top secret. Not only in the guidance, the weapon systems, they're using machine learning algorithms, but now they're starting to use them to predict where likely terrorist cells are, whether it's on our homeland or in foreign countries. And they're having incredible success doing it. So they're working with the intelligence agencies, also the special forces. Because if you think about it, the future of warfare is really an intelligence game, isn't it? It's not so much a big army. I don't think we're ever going to fight a big tank war again. It's not like, I don't think we're ever going to fight a huge army like Russia or China. It's going to be small, special force, type of limited engagements. And I think that in the future, machine learning will be utilized for what's called swarm theory, swarm learning theory. So we'll build a bunch of drones, but probably very, very small, but they'll operate in swarms of thousands. And they'll operate autonomously based on how we program them, but they'll be bringing in new data at all times to the machine learning algorithms and improving, what they need to do in partnership with humans. Well, that's very, very scary. There are a lot of ethical issues involved with that, but I think that's where it's headed.
I'm at the Da Vinci Institute, which Thomas Fry is, the head brain of, and he's talking about the personalized programs and how everything is going to end up. There's going to be just hundreds of options.
Yeah, absolutely. I guess my point here is that we're going to be creating these drones that take in new data and actually changes the swarm of drones objective based on that data, but it's still programmed in the beginning by a human. So if the human doesn't get it right, a lot of bad things can happen. So we need to think real carefully about this. But I'm telling you, this is what's happening now. This is where it's going. Walmart is using decision support systems a lot to actually revitalize their supply chain management system, but also to figure out how to move goods. Maybe they have chairs that aren't selling, so they'll start moving them to different areas in the store and keeping track of it. And if they put it in one area of the store and they're selling more, they will record that and use that information to help move other items that aren't selling. Goldman Sachs is using decision support systems to help them decide what trades to make, also how to design and sell different financial products, and it's working. FedEx is using it to market to different businesses, to different segments, but also through logistics. Last but not least, IBM Watson has an entire $1 billion business around using machine learning algorithms to help in healthcare and other consultancy endeavors. I think that they're on the right track, but Watson may be too expensive and may be the experiment. And I urge you, if you want to experience the future and get involved in an area that's going to be a great career, you can make a lot of money doing this because you're adding a lot of value to others. You can use open source tools to create something that will rival Watson. There are many machine learning open source algorithms that you can access today. You can build high performance computing systems. And I see this as revolutionizing businesses and government and individuals on a personal level. Thank you. Any questions? Yeah, it is. I think that they're having some pains right now. I'm not sure why.
They have such a huge tool, like this huge camera, and
yeah, I think what we're missing, I think really the engineers are ahead of the business process people. So I think what we're missing are really good business process people to come in with teams with the data engineers and the data scientists, and to be, because it's very domain specific. I can tell you, just working in it, if you don't understand the business and knowledge processes, and not only where the company is at now, the organization's at now, but where it needs to be in 2 or 3 years, you can't add a whole lot of value, right? You need to understand that at a very, very deep level. So it's almost like the technology and the engineering is way ahead of the knowledge and business processes, but you need to put that all together into a team to be effective. Any other questions? Yes?
It's getting super late, so hopefully this is quick, but there seems to be a debate amongst data scientists as to how well you have to be an infrastructure person, like I asked last time Mongo and NoSQL. As this develops, do you think you're going to add a ton of infrastructure people and let the data scientists do the thing, or if you're trying to get into the industry now, is infrastructure really the thing to learn in depth?
Well, I think that there's always room for data engineers building infrastructure. They're a very, very important part of it, but in my experience, I don't think you should start with the technology or the infrastructure first. What I suggest doing is starting with the business. What is your business model? Where are your clients today? What are your products today? Where do you want to be in 3 or 4 years? I've come into situations where they spent millions of dollars on technology and infrastructure, hired a bunch of data scientists, and they're getting absolutely nothing out of the data because they didn't do the hard work of thinking, what business are they in? What data do we need to help us do what? At the operational level, at the tactical level, at the strategic level. What business problem are we attempting to solve? Remember, it's a partnership between human and machine. And so what you want to do is create or build an analytical eco-structure that provides data to people so that they're making better decisions. Because at the end of the day, data science is about helping people and organizations optimize their decision making. And if you don't do that, then as a data scientist, you're not really adding any value, right? And so you can build a huge infrastructure put tons of data through it and hire hundreds of the best data scientists in the world. If you don't understand how it's helping your people in your organization make better decisions and how it's helping your people conceptualize things differently. So remember, the question when I ask when you join the data science meetup is, what truth do you know that few other people agree with you on? That's really the key thing as a data scientist. If you really want to earn your money as a data scientist, it's to find truths that nobody else knows, right? That's the huge value. It's not just the technology, it's not just the data. Remember, we took a look at that and found out, the data doesn't speak for itself. You have humans interpret the data, right? And data is not objective, right? It's all biased because it's collected, curated, manipulated by humans, and we humans are flawed. I'm biased. I got to be really careful. But when I do work, because I bring a bias, and I try to check it, but I'm not good enough to do that. So I need my colleagues. Mike always checks my work. I always ask him, and a lot of times Mike finds stuff that I didn't think about, but it's not because I intended or because I'm stupid, but because I have some sort of a bias, a blind spot. And that's why I preach teamwork, because we need trusted people. I don't have an ego. Mike doesn't have an ego. Mike will ask me the same thing, and it's not me tearing into Mike. We're helping each other, right? And unless you have that in your organization, you're not going to get the full benefits out of data science or data engineering. So it's not just an infrastructure problem. Infrastructure is very important. Data engineers are extremely important. Data scientists are important. Domain experts are important. Data analysts are important. But in a team environment, if that makes any sense. Sam?
Yeah, I don't know if I understood your question, but how important is it to know the infrastructure? I kind of forgot the question, but the way I heard it, the answer I would give you is that usually the bigger the team, the more they have people dedicated Spark if you're the data scientist, but in terms of maintaining a cluster of Spark machines and knowing how to maintain the data and all that stuff, usually the bigger the effort, the more they can afford and the more they need people who are dedicated to supporting just the infrastructure, and you don't need to know that so much. I'm sure you know.
Yeah. Well, it also depends. I mean, in a lot of startups, they'll hire a data scientist and they'll expect the data scientist to be a data engineer, to be able to understand the Hadoop ecosystem, Spark, Apache Spark, to be able to be a programmer. And there's just no way a data scientist can know all that. I mean, there's maybe half a dozen geniuses in the world, but they're unicorns and that's it. The rest of us are normal.
There's no such thing as a full stack data scientist.
Right, thank you. Yeah, right. So, you know, right, and so we've learned in the last few years, you know, especially in larger organizations, it's teamwork. You have to specialize, and it's very, very difficult because a lot of data engineers, they're very, very intelligent people. Data scientists are very intelligent people, and they like working alone because they prefer to rely on themselves, right? Because they know their work, you know, is good. But you have to start working in teams, and that means, as in any team, communication, helping your teammate. And that's a different skill set. So I often tell data scientists today, I don't care how brilliant you are, if you can't operate in a team environment, then you're probably not going to be successful as a data scientist. But because it just won't work, you know. And remember, the bottom line is that you've got to get the results of the data science to members of the organization so they can make better decisions. Some data scientists are brilliant, they just can't get it, they can't communicate. Some data engineers don't get it, they can't communicate with other people, they can't work with the data scientists. And it just, you know, you don't get the full value out of the data science. Yeah.
So, I assume the rule that Sankey had where it was like for data science.
Yes.
It's like a high
Yeah.
Where do you think we are along that?
That's a great question. Mike and I have debated a lot about this, and I think, this is just my opinion, I may be wrong. The term data science has been bastardized already. So it's hyped. You know, a lot of people think data science, or a data scientist is some universe of genius who can program, who can do data engineering, build you a high-performance computing system, and develop these formulas that's going to design the latest product that everybody's going to want to buy and rescue your company, you know, from bankruptcy. And you know, it's just false. We all know that. Now, data scientists and data engineers can add huge value, right? But not to that extent. We're not magicians, right? So I think that a lot of the hype that went on with big data has now been transferred on to the term data science. So people, when I go out with clients, they're very confused. They say, what the hell is data science? And it's a vague term, so I think we need to define it better. I think we need to distinguish data science from traditional data analytics. And I define it by data scientists use the scientific method. And they're trained to understand all the traps and different biases that you can find in the data. And you can design and execute these machine learning algorithms and understand it at a very high conceptual level. And once you start to understand it at a high conceptual level, it kind of sucks. It takes a lot of the fun out of it because you realize how much can go wrong. You know, and you realize how much you need a team of people to help you, especially in the domain area. So I think we're at the peak. And I think we're going to go into a valley in the next few years because it's been hyped out. I fear that many organizations aren't doing it right. they're buying the technology first without understanding their business problems. They're not distinguishing between the data science and the traditional descriptive data analytics. And that can have value, don't get me wrong, it's not the same. And so they're getting very little, if anything, out of this data. And I'm already talking to leaders in organizations who are saying, I just spent millions of dollars on all this technology, and we're not getting any value out of the data. So there's a lot, that's what's going to cause it to peak and then go down. And then eventually people will realize there is a right way to do it. They'll call you, they'll call me, and they'll say, okay, this is the right way to do it. It's hard, it's a challenge. We need a team of different people. We need a guy like Tom, we need a guy like Mike, we need a guy like Andrew, we need a guy like Jay. And put them together, and then we need to really think through what the business is, how we're going to add value, right? And how people make decisions and how we can augment human intelligence so that they can make better decisions. And that's not an easy thing, but that's what adds the value. That's what makes the competitive advantage. And then using the machine learning techniques that these companies are using, again, I think it's like the Neanderthals. You either adapt, organizations are either going to adapt and use machine learning algorithms, data science, computing to augment their intelligence and therefore get competitive advantage, or they're going to go the way of the Neanderthals. I think they will start to go out of business or go so far behind they won't be competitive anymore. And that will force a huge change. So right now, it's in its infancy. You see the leaders here that are starting to do it. The others are able to get by, but as it gets better and better, those laggards, the organizations that don't apply these techniques, I don't think that they'll survive. I think they go the way of the Neanderthal. And that means that you all have the Full Employment Act, right? They're going to need us, to help them do it the right way once they get away from the hype of, you can buy the technology, add a little data, push the button, and voila, you're going to have some sort of competitive advantage. That's what they've been sold. So, I don't know, Mike, what do you think? In the next year, data science will start to go into the valley of death, the trough? Or is it a couple years away? What do you guys think?
It's going to be now.
Is right now? Yeah, Mike may be right. He's usually better at predicting these things than I am, at least the time. I think he may be right. I was going to say in a year, but I think it's peaked, and because the organizations aren't getting anything out of it, or they're getting a little bit, but not enough to justify the money they've spent and the headache they've spent, to do it. So it's weak ROI, return on investment. And how long do you think it'll last? 2-3 years?
Okay, so to give you a sneak preview on next week's blog post,
okay,
there's a divergence in popularity between the terms data science and data scientist. Everybody wants to do data science, but nobody wants to hire a data scientist.
Yeah. That's a great insight. You're right. Yeah, you speak up, because that's a really interesting insight.
So on Google Trends, the comparison between the term data science and data scientist diverge. So everybody wants to do data science, but nobody wants to hire a data scientist.
Well, and I think there's confusion. Will the real data scientist please stand up? I think a lot of people are now calling themselves data scientists, and they probably aren't doing data science. They're probably doing traditional data analytics work that they want to raise, or they want to feel important. We all do. I want to feel important too. So, Tom, what do you think?
Well, you could say a data scientist is someone whose ego's been hyped up by big data, like they do with Sparks. Just because you can do big data doesn't mean it's a good idea. Which goes back to another one of my from previous blog posts. Yeah, read his blog up to that.
Yeah, you guys gotta read Mike's blogs. I read them,
read his
and
blog.
they're full of great insights, just different angles of thinking of things. So do you think that data science, the term, is actually going to...
I think big data is not getting the ROI because people are just jumping into it without really, getting their hands, feeling it. Overall, I think it's going to do good because, like you showed, there's just so many places it's going. So some of it, I